Up until now, VLANs feel clean. One switch, multiple VLANs, broadcasts stay contained, and everything behaves exactly how you would expect. But then you think, okay, but what happens when I add another switch? You connect the cable, and suddenly people start wondering, does the VLAN still exist? How does the other switch know? How does traffic stay separated? And why doesn't everything collapse into one big flat network again? This is the moment where VLANs stop feeling intuitive and start feeling mysterious. This video exists for that exact moment, not to show commands, not to quote standards, but to remove the confusion logically. The confusion comes from a hidden assumption. Most beginners, without realizing, think a VLAN lives inside a switch. And that feels true at first. You configure it on a switch, you see it on a switch, you talk about VLANs on a switch, but that mental model is incomplete. A VLAN is not owned by a switch. A VLAN is a logical identity, and logical identities are allowed to span hardware. Once you fix this idea, everything else stops being confusing. Let's build the simplest real scenario. You have switch A, switch B, and a cable connecting them. On both switches, VLAN 10 exists. Devices are assigned to VLAN 10. Now here is the requirement, and it's non-negotiable. Devices in VLAN 10 must behave as if they are on the same local area network. Even though they're on different switches, even though there's a link in between. That means same broadcast domain, same logical network world. So now we can ask the real question. How does VLAN 10 survive the journey between switches? Now imagine VLAN identity is not preserved. A frame leaves switch A. It crosses the cable and it arrives on switch B. But it arrives with no VLAN context. Switch B now has a problem. It doesn't know which VLAN this frame belongs to, which broadcast domain it came from, or how it should be treated. So the only thing it can assume is this is just normal Ethernet traffic. And that assumption destroys everything. Broadcast leak, separation collapses, VLAN silently stop existing. So now we know something important. VLAN identity must not be lost. This leads to a core rule. A rule so important that VLAN cannot exist without it. When traffic moves between switches, VLAN identity must travel with the frame. If it does not, switches cannot enforce separation, VLANs cannot span switches, and the entire design fails. This isn't an optimization, it's a hard requirement. So now the question becomes, how does VLAN meaning actually travel? Before we answer that, let's look at the easy case. Inside a single switch, a port connected to a PC belongs to one VLAN. So when a frame enters, the switch already knows the VLAN. No extra information is needed. The port itself provides the context. That's why VLANs feel simple. When you're only thinking about one switch. Now look at the link between switches. This link is like a PC connection. A PC belongs to one VLAN, sends normal Ethernet frames. A switch handles many VLANs at once, so this single cable must carry VLAN 10, VLAN 20, and VLAN 30 traffic, all at the same time. And the receiving switch must be able to tell them apart. That's why inter-switch links are logically special. Here's the big idea, conceptually. Some traffic is untagged and no VLAN identity is attached. And some traffic is tagged, with VLAN identity travels with the frame. End devices send untagged traffic, receive untagged traffic, and do not understand VLANs. Switch-to-switch links carry tagged traffic, so VLAN meaning survives the journey. This distinction is everything. Here's the full picture. A PC sends a normal Ethernet frame. No VLAN label, just data. The switch knows the VLAN internally, adds a VLAN identity before sending it across the inter-switch link. The receiving switch reads the VLAN identity, places the frame into the correct logical bucket. Before sending it to another PC, the VLAN information is removed. And devices never see VLANs. VLANs exist inside the switching fabric. They are switch side illusion, and that's intentional. Now imagine this breaks. Switch A sends VLAN 10 traffic. The link strips the identity. Switch B receives plain Ethernet. What happens? Broadcast leak. Devices hear traffic they shouldn't. Logical walls disappear. The network looks connected, but VLANs are gone. This is why tagging is not optional. Without it, VLANs collapse the moment you add a second switch. Now lock this in. If VLAN 10 exists on switch A and VLAN 10 exists on switch B, VLAN identity is preserved. Then, VLAN 10 is one broadcast domain across both switches. Broadcasts cross the inter-switch link, but only inside VLAN 10. They do not leak into another VLAN. The boundary is logical, not physical. Earlier you learned that switches flood broadcast. That is still true. Here's the refinement. Switches flood broadcast inside the same VLAN. VLANs redefine what everyone means. Everyone now means everyone in this VLAN. Nothing contradicts earlier lessons. VLANs add structure. They don't break rules. Think of two office buildings connected by a hallway. Inside each building, multiple departments. The hallway carries people from all departments, but everyone wears a colored badge. At the entrance, guards check the badge and send people to the right department. If badges didn't exist, everyone would mix. Departments would collapse. The badge is the VLAN identity. Why not let routers handle this? Because routers add delay, add complexity, and weren't designed for internal switch fabric. VLANs let switches stay fast, stay simple, but still scale logically. They extend layer 2 without turning it into chaos. Let's clear the traps people fall into right here. A VLAN ends at a switch. No, it can span switches. A switch link is just a normal cable. Physically yes, but logically no. Tags are advanced. No, they're required. If VLAN numbers match, it's fine. No, identity must be preserved in transit. Let's lock this in. VLANs are logical networks. They can span multiple switches. Same VLAN across switches equals one broadcast domain. Inter-switch links carry multiple VLANs. VLAN identity travels with the frame. End devices never see it. If VLAN identity were not preserved, VLANs would die the moment a second switch was added. And that is why this video matters.